Hello and welcome to Mathematics for Everyone, Episode 2. Today we want to talk about a broad topic. This is the topic of philosophy of mathematics and physics. Now, you might think that this is a podcast or basically like a series about mathematics. What does physics do here? But physics is important for mathematics and mathematics is important for physics. And there's actually a lot to be learned not just in the field of physics, but also for mathematics. Now, what we are going to do today is to talk about a bit more in a general sense what kind of mathematics and physics even is. And for this, we are going to cover some examples which are not readily available for everyone. But this does not, or this should not, distract from the main point that we try to preserve. Now, as I've already mentioned, what actually is mathematics and physics? You could answer this question in loads of ways. I'm sorry for that last one there. That wasn't very pretty. You could answer these questions in a lot of ways. That wasn't a sentence. You could answer this question in a lot of ways. Now, one of my favorite points of views on mathematics and physics is that mathematics is a language of ideas and logic. So this is the first important point, that mathematics is actually a language. And it is a language for ideas and logic. So mathematics is, as a language, kind of independent of other sciences, except for maybe logic, if you want to think about that as a science, then as a sub-science of basically philosophy. But mathematics can be used as a building block for other sciences, for example, physics. Now, how I like to think about physics is how physics is often not even taught, which is kind of a shame if you ask me. But physics, from my point of view, is thought of as the science of interpreting mathematics. So physics is the science of interpreting mathematics. What do I mean by that? Now, mathematics is in and of itself a very beautiful language. But usually, when you have a language, you can write poetry, which for me is mathematics. But not only the intrinsic beauty of this poetry and of mathematics is our drive for mathematics, but it's also the ideas that are being conveyed. For example, if you want to write a poem about your beautiful wife, then not only are the words important that you use, but also the meaning that you get across. And physics is the science of this meaning. So basically, mathematics is the poetry in and of itself, and physics is the meaning behind the poetry. Now, as an example for this, you could look at two very basic equations. I hope this illustrates what I mean by interpreting versus just as a language for ideas and logic. Now, if you think about a plus b squared, then this is a squared plus 2ab plus b squared. This is readily proven just because a plus b times a plus b is by the distributive law, this plus this, right? So this times this plus this whole thing times b. So this would be a plus b plus b, a plus b. It doesn't really matter where you put the a plus b, on the right hand or on the left hand side, because we have the commutative law for multiplication. But yeah. So this is a times a plus a times b. So a squared plus ab. This is b times a. And again, you can write this as ab due to the commutative law. And this becomes a squared plus 2ab plus b squared. Now what I did here was a form of mathematics. I expressed an idea. And the idea is this this square of the sum basically you could say the square of the sum is not equal to the sum of the squares, which is an important implication of this. But more explicitly is equal to the sum of the squares plus a correction term, right? Or plus like a kind of a coupling term. And this is where interpreting comes into play. I've already done this kind of instinctively because of me interpreting this 2ab as a coupling term. I've already done something that is very important in physics, is giving these terms some meaning. And by coupling, I mean something like A and B both have influence on each other. And as you can see, if you have a large quantity here and you add something, you still get a large quantity here due to A being large. So this is kind of a coupling term, and the square of the sums, or I shouldn't say the square of the sums, but the square of the sum gets represented by this, or actually by this whole thing, because it's the square of the sum. And equal to the sum of the squares, which is this. So what I've done here is I have taken this idea and translated it into mathematics, into the language of symbols, etc. So the basic idea behind mathematics is the path from here to here. So this path. And in order to go this path, in order to be able to show this relationship, right, you have to use logic and algebra and all these good things that the language of math provides for you. But the ideas behind it can be formulated in a mathematical context as well. Before I go any further, because this was kind of the wrong way of thinking about this, or not the wrong way, but kind of the backwards way of thinking about this, we can also think about the metric. For example, let D be the Euclidean metric, which means Euclidean distance, in R2. So basically what I'm saying is we have 2 points, and I'm just looking at their distance. which would be this. Now, what you can define the Euclidean metric in a way, but if you say, oh, I'm at a point A here, and I want to go to the right, kind of way, and this would be X and Y. How do you do that? Sorry for that. So how do you go express, how do you express the idea of going to the right? This is where mathematics comes into play. I have this idea in mind, going to the right, and I have to think about how do I model this, and the model that I can use, or the language my model will be written in, is mathematics. So let's think about this. Well, to the right would mean along the x-axis, right? So what you could do is you could take A and displace it a little bit. So going to the right would mean going to the right becomes adding something, adding this vector. And as you can see, this vector is just parallel to this vector here, to the unit vector in x. So what you could say is A plus x. But not only plus x, plus some quantity. Let's say, let's give this quantity a name. Let's say this is h, and h is just the length of this. So you can type h times the unit vector along x. This would be going to the right of A, basically, right? This idea, going to the right of A, or yeah, how we express this is with the language of mathematics. Right would mean plus in this case, because h would be positive, and going to the right also, yeah, just means plus. I'm sorry, that was redundant. The plus here means going to the right. Because as you can see, going to the left would mean adding a minus ex. So just reversing the orientation of the unit vector in x direction. So this part was again mathematics. The idea of going to the right was in our mind. We wanted to do that for whatever reason. But you can express that in this way. Now, to get back to what our Euclidean metric does for us, what you want to have happen is that the distance becomes bigger. So if you have these two vectors, you want the distance, so this vector being longer than this vector, basically, right? You could check for the length. You could use the Euclidean metric for this. And this is very interesting because mathematics was used here as a term or as a way of interpreting and translating. Now this is quite funny actually to me because this is also translation, but whatever, doesn't really matter now. And what I've done here, so if you had this formula and you go the other way around, would be physics. And to see this, let's look at another equation. Let's look at the equation a squared plus b squared plus c squared. No, not plus c squared. Equals c squared. Now this is quite a famous formula, But in and of itself, it doesn't mean anything. It doesn't even have to be true. For example, if A is equal to 5 and B is equal to 5, then C is equal to 7, it's not true. Because this would be 25, so 5 squared is 25, plus 25 is equal to 50, and it's not 49. So this doesn't make any sense for any arbitrary numbers, whereas this above, like this right here, makes sense for any given number, which is also a difference between mathematics and physics, kind of generality. But this is a mathematical formula, we can all agree on that. The question is, why is this behaving differently than the binomial law that we had above? Well, the answer is that this equation has to be interpreted. What do I mean by that? Well, it has to be interpreted in the setting of right triangles. Sorry, that is not a good T. Right triangles. Then this makes sense. Because if you think about that is not a right triangle. If you think about a right triangle, and this would be A, this would be B, and this would be C, then the equation that is sketched above makes sense in the idealized case. So, physics, in a way, has to be interpreted as well. And to see this being the case for actual physical equations, let's look at the Maxwell equations. And you will see what I mean, or you will see why I brought up the Pythagorean theorem. So for example, the Maxwell equations in differential form would be the divergence of the electric field being equal to the density divided by the, I don't know how to say this in English, influence constant or something. Then the divergence of the magnetic field being equal to 0, the rotation of the electric field being equal to minus the time derivative of the magnetic, the change in magnetic field basically, and the rotation of the magnetic field being equal to some constant times J plus the change, and this is the important bit, the change of the electric field in time. Now, what I've said before, this doesn't hold for arbitrary E, B, and rho, for example. Because it wouldn't make any sense. For example, E could be something that is not even differentiable. But this equation is correct when interpreted in the right setting. And the setting it has to be interpreted in is electromagnetism. Now, why is this such a good example for interpreting mathematics, or basically physics being a science of interpreting mathematics? Well, we can assign a certain idea behind every equation that we obtain. And this is what physics is about. The equation, divergence of the magnetic field being equal to 0, is mathematically not very interesting. Because it's a property of the magnetic field, fine, whatever. But physically, it's very interesting, because this means that the magnetic field has no source. So what we've done now is we've done physics. and doing physics is interpreting a mathematical equation. Here being that magnetic field, or there are no magnetic sources. Basically, there are no monopoles. Right? So the electromagnetic field has no source. This is an incredible thing. And in order to obtain this information, in order to draw conclusions from electromagnetism, we have to interpret the mathematical equation that is given. In the same way, we can interpret the divergence of the electric field being the charge density, which makes a whole lot of sense, because this just means that the sources for or the sources for an electronic, that doesn't sound right, electric field is equal to charge, which is the definition of what charge should be. So this equation makes sense not only because it's mathematically valid, but because our interpretation of them in a physical context makes sense to us. If we obtained anything else, we would be screwed. Physics would be kind of screwed. There is even another step. The subtlety goes even further in physics. And I'm sorry for the hit there. The subtlety goes even further with this minus sign. Now, if we apply the physics idea, right? So if we just say, hey, we are doing physics again, and we take the rotation of the electric field being equal in some way to the change in the magnetic field, we could say, well, there is the principle of induction. Change in magnetic field induces a change in electric field, and the fourth Maxwell equation says a change in time of an electric field induces a change in a magnetic field, and more importantly, induces a magnetic field. Because if there is a change in something, there has to be something. But this goes even further, because physics has to do with the sign in front of it too. So the other important information here is Lenz's law. Because this minus sign actually has a meaning, not only mathematically, but from a physical point of view. Because this induction means that that what is induced is opposite to the inducing. Basically, this is the idea behind braking, like actually coming to a halt using electromagnetism. So even as subtle as a minus sign can be so important in physics, because otherwise things would fall apart, like heavily. So physics is actually the finding the right interpretation for the mathematical equations. Now, there is some philosophy that has to be discussed here. Not only that physics in this way has to start from somewhere and then in going somewhere else has to do physics. What I mean by this is usually in mathematics we start from a set of axioms that we all agree are true, and we deduce something using some simple logic and algebra and whatnot to obtain something that wasn't there before. For example, if you start with just the laws of the field of real numbers, you could prove, as I've did before, the binomial formula. But in physics, this is kind of a different route. Physics takes the axioms of mathematics, but not in this generality. For example, we can take the Schrödinger equation as a postulate and just run with it and see how far we go. Because the important point is not really the rigorous starting from the ground up mathematics, it's the interpretation that can be done with what we have. Now there's another interesting philosophical point to be discussed, and that is basic mathematics, the formulas are just plain white wrong in the real world. What I mean by this, for example, is there is no right triangle in the real world. Because let's draw this, and let's assume I did this quite. Let's assume I did this perfectly, even if I did all these strokes perfectly. This would still not be a 90-degree angle. This would, like, we couldn't even measure length in this kind of sense. Because all of this has a thickness to it that we can't get rid of. And no matter where we draw or what we draw, we can never draw a perfect right triangle. So Pythagorean, or the Pythagorean theorem, only holds for the ideal right triangle, right? For the actual right triangle. And this is nothing to be ashamed about or sad about, because mathematics is the language of ideas, as I've said before. And this is why I've said that it is the language of ideas, because mathematical equations hold in an idealized setting where we have an actual right triangle, for example. The same can be said for physical formulas, where these Maxwell equations, for example, hold and are very important, but kind of drop some cases. For example, there is no quantum mechanics here. There's nothing that is done in terms of quantum electrodynamics. There's nothing in terms of non-classical physics here, because this is just plain classical physics. So, in this sense, these formulas don't actually hold in a perfect environment, because there's always something that is missing. And we can argue that we can never really get to a point where everything is perfect. Now, is this bad? No, it's really not, because even some differences will not be noticeable. And that's very much fine. Like if we apply physics to engineering or to chemistry or whatever, it is very much okay that there is some form of error involved, as long as the error is small enough. And in the same way, using the Pythagorean theorem, it's not a perfect thing, because as long as you can draw it and stuff, or build it, it won't be exact. Now, this really shouldn't be disheartening, because it's fine. Mathematics in and of itself is appreciated for its beauty in its rigor, and physics is appreciated for the same thing with an interpreted case. Now, usually when one studies physics and one is mathematically inclined, one encounters a problem where mathematical rigor fails to apply in physical in the physical world, because mathematical rigor is too rigorous for physics. What I want to talk about is two principles, one principle for mathematics and one principle for physics that highlights this difference. So, on the one hand, we have the principle, whatever, the principle of generalization, in mathematics. And on the other hand, you have the principle of multiple perspectives, as I like to call it. In physics. And we're going to discuss each of them in detail. Let's start with the principle of generalization in mathematics. Now, what can you say about generalization, and why is it such an important tool in mathematics? I will focus on one specific example of generalization where I think you can really see the steps that are taken in the mathematical way and in the mathematical sense in order to arrive at a meaningful mathematical conclusion. Now, let's look at the following rule of differentiation. If we have two functions f and g, and we want to take their derivative, principled or basic calculus tells us that this is given as df prime plus g prime f, or fg prime, whatever you want to do. So this holds for all f and g that are at least c1, for example. So they're at least continuously differentiable once. And this is totally fine. It works every time. Now, usually when we study calculus, for example, we are interested in studying differential equations. A differential equation could, for example, be something along the lines of the second derivative of a function is given in terms of the function itself, with maybe a minus sign. This could be a differential equation. But maybe you have more difficult differential equations where you have both dependencies. So if you have a function that is dependent on one time variable and you add to it the second derivative of the space variables, maybe this is something interesting. Right? You can study these kinds of equations and these become very difficult very soon. If you want to find a function that is continuously differentiable, at least once, for example, that satisfies this equation, maybe you'll have a tough time. Maybe it's more important for us, if we want to find a function, to maybe say, oh, I have a bunch of stuff that satisfies something that looks like that looks like my equation. And then afterwards, I can say, okay, now I can sort through these and not through all of the functions that I need. So generalization is actually a tool for breaking up a problem, at least in this case, breaking up a problem into something more manageable. And what I want to talk about is a weak solution to a partial differential equation. Now, a partial differential equation means that you have partial derivatives, such as these. And at this point, I'm pretty sure that people who are listening are familiar with partial differential equations, or at least with partial derivatives. Now, if you have a function that is C1 and satisfies this partial differential equation, then it will for sure satisfy the integration by parts, or basically the product rule for functions, right? For once continuously differentiable functions. So, if you have a C1 solution, then it satisfies the product rule. Right? So if you have a C1 function that solves my differential equation, it satisfies the product rule. So this is a one-sided implication. C1 function that solves it implies it's satisfying the product rule. The other way does not necessarily hold. Oh wait, the other way is not necessarily true, because not every single function that satisfies the product rule also is a C1 solution for my differential equation. So this means satisfying the product rule is necessary. Satisfying the product rule is a necessary condition. Which means if we find out something that looks like a solution to our differential equation and it satisfies the product rule, then maybe we can find in these that we have found that we will call weak solutions a function that is even stronger than this. What I mean by this is we have to put this into a setting where we can actually work with the product rule. And potentially, if we have a function that is once differentiable, maybe it's not even twice differentiable, right? It doesn't have to be. So this product rule becomes an integration rule. This means the integration of f times g dx. I will kind of not introduce notation. I think this is given by the context quite understandable. Fg dx plus g prime f dx. What you could do is the integration basically being the inverse of the derivative using the main theorem of differential and integral calculus. You can see this is basically f and g in the boundary terms, and the left side becomes an integral. The right hand side has these integrals. So what you could do is you could say the integral f prime g dx is equal to the boundary terms of f times g minus them swapped around. This is what's called integration by parts, where you integrate the first and differentiate the second. And you can kind of eradicate g, and at some point maybe you can evaluate this integral, and then you have your integral that you want. For example, sine and cosine have the famous property that their second derivative is negative their original function. So what you could do is you could apply this twice and then put it to the other side. And these are some interesting and nice ideas for how you can find the solution to these equations, or to just finding an integral. But What we would like to do is any function that satisfies the product rule also satisfies the integration by parts. So product rule implies integration by parts. So what we can do is, if my function is a C1 solution, then it satisfies the product rule. And if it satisfies the product rule, then it satisfies integration by parts, which means that if we have a C1 solution, it satisfies integration by parts. Now, this can be used to model what we will call a weak solution. Because if you take this solution, for example, up here, right? du by dt and d squared u by dxx, then this equation becomes if we multiply with a function. So first what we're going to do is we multiply with phi, and phi has to be chosen suitable, but we'll not go into detail here, and integrate. So phi du dt plus, or dx, then we integrate by dt, for example, and this has phi du dx dt is equal to 0. What you could do is you can do integration by parts. And what you obtain is that the integration of u times d phi dt plus phi, we don't change the second for now because we focus on the first. What you've done here is we've swapped the differential. Now this can only be done if the boundary terms vanish, and this is how we choose phi to be. We choose phi that this actually works. But what we've done, we've transferred this differential, and this is the function that we are actually looking for. So if we see that this function satisfies this equation for every phi, maybe we can find a strong or a solution to our differential equation here. Because a solution to our differential equation definitely satisfies this. But now, if we just solve this equation, and it may seem that this is way more complex, but it's not, maybe we can find a solution that was good enough for my original equation. So this is a bit crude and it's not exact, but I want to give you a taste of this. We say that U is a weak solution. Why do we say that it's a weak solution? And this is what mathematics does with generalizing. Is we have taken a strong solution in a way that this is C1 being strong, then it satisfies the product rule and it satisfies integration by parts. But if it satisfies integration by parts, it definitely satisfies this equation for every single phi there is that is chosen appropriately. So as long as we have a strong solution, it definitely satisfies this. But this is a solution, or this is an equation that is way easier than the original one. So solve this. And once you solve this, you can sort through the chaff, right? You can just say, okay, I'm not really interested in this u and this u. Oh, I found a good one, right? So, solve this easier equation. And sort the solutions to find a solution to your original equation. And we don't ask whether or not this is always possible, for example, but this definitely makes our life easier because now we can develop tools. Whoops. Now we can develop tools mathematically to solve the easier equation and tools for sorting. So what we've kind of done is we have generalized to a point where we have an easier equation, solved this easier equation, and then looked at what kind of functions satisfy my original requirement. And the important step is what kind of function satisfies the original requirement, obviously, because this is the hard part, but we have done some simplifying. This may be very much for this might be just very abstract and very deep, but think about it like this. For anyone who has seen my last video, you will know that we've talked about a equation in number theory where we have x squared plus y squared plus z squared, just draw a line here, plus x plus y plus z being equal to 1. And we've asked ourselves if x, y, and z are just some whole numbers, yeah, do these exist, right? Does there exist an x, y, and z such that this equation holds? What we found out by simplifying is that it can't be. Because, and this is the same abstraction that we've done up here, every solution to this satisfies the equation modulo some number. Because, as you can recall, as long as both sides are equal, they're both just whole numbers, they have to be the same for every single number there is when you look at the modular arithmetic with respect to the number that you choose. For example, with 2, we've seen if these are equal, both sides have to be odd, because 1 is an odd number. So this one has to be an odd number all the time, or for the solution that we are interested in. And we found out that this is not the case, because if no matter what x, y, and z are, x squared plus x is always an even number, because even squared gives even, plus even gives even, and the same for odd. So what we found out by simplifying, we found out that this just can't be. So every solution has to satisfy. So solve the easier equations. The easier kind of modulo equations, and sort through the rest. Because they are modulo solutions, we we have kind of put a bunch of stuff into one single category, and then we kind of have to sort through the categories to see if there's actually something worthwhile there. So let's sketch this. What we've done is, if you have a C1 solution, then it satisfies the product rule, it satisfies integration by parts, and it satisfies this. So, same here. Every solution satisfies the same equation modulo the same number on both sides. So what we do is we solve the easier equation and sort through the solution. So what you see here is this simple principle that is very apparent in number theory seems so distant up here when thinking about calculus. This is a philosophical standpoint in mathematics. If you have a field that is working on some principles, for example, number theory is working on this kind of principle where modular arithmetic is something you think about naturally, then why should it be, or shouldn't it be, natural to think about the same thing in other mathematical contexts, right? So what we can learn here is a mathematical philosophical principle of generalization. And not only generalization, oh, wait, no, wait, I don't know how it's written, actually, I'm embarrassed. What the, no. Oh, principle of generalization. I think, yes, I think. Oh my goodness, this is horrible. Just kind of like this. Mathematical principle of generalization, and kind of transferring. What I mean by this is the same generalization I don't know, actually. I really don't know. I think this actually wait, just wait. Just wait. Wait. Generalization. Wait, what? Generalization. I knew it. I knew it. It had to be an E, right? Yeah, it had to be an E, and then it had to be an A here. Okay, this is embarrassing. It's very embarrassing. Generalization. Just like the general. Oh well. Well, whatever. So the same generalization doesn't come in the same natural way in every field of mathematics. So how you could say this is the same generalization comes, oh, maybe the same generalization that comes naturally in one field might not be so obvious in the other. But is there. This is the important part. If you work in mathematics And you know that there is a principle in number theory, for example, looking at um, numbers in modular arithmetic, and then you ask yourselves, wait, why can't I apply this? And of course, maybe you can't apply modular arithmetic. Of course, you can't apply modular arithmetic to this. But the important part is you can apply or use the basic principle that is behind it, that every solution satisfies some more specific equations. So this is a one-way implication. And then you solve the simpler stuff. And once you've solved the simpler stuff, you sort through the stuff that is not interesting to you. And this is what is also very important in physics. And this is where we come to a point where we want to describe the principle of multiple perspectives in physics that is something that we see here already. Because this is also, in a way, a principle of multiple perspectives, something we will see in physics just in a minute. Same viewpoint, same principle in different lights. So mathematics is about ideas, and this seems to be a very important idea. Because it had an immense impact on two fields of mathematics, just because it was the same idea, which means it's important. That last sentence didn't make any sense, but whatever. Let's talk about physics. Now, in physics, we can discuss the principle of multiple perspectives, as I said before. What do I mean by that? Physical principle of multiple perspectives. And this is something that Richard Feynman is very noted for, or at least I have learned this kind of thinking from Richard Feynman and from his famous lectures, is where physics depends on nature. And we don't know how nature does its stuff. Oops, that is really not a word in the English language. And we really don't know how nature does its stuff. If we have two theories that perform in the same manner, we have no clue which one of them is correct, right? So, given two theories, who produce the same output, produce the same results, we can't choose one over the other. Now, as I've said before, up above, maybe you can find, maybe you can prove that there is no solution to the equation x squared and so on and so forth by just having an ingenious idea and not going the modular route. This is fair and completely fine, but if you have two proofs which produce the same accurate result, you cannot choose between one or the other. The only point of discussion where you could choose would be personal taste and also how it fits into your work. And this is what Feynman talked about when he talked about equations of motion. Because when we talk about equations of motion, you have multiple formalisms that are applicable. Now, there's an example that Richard Feynman gives in his lectures that is basically just Newtonian physics, where you have the simple idea of solving a falling ball problem, for example, just in simple F equals ma. This is one possible formalism for this. But there also is the Lagrangian formalism, so this would be Newton. But over here, Lagrange would do something different. You would see, okay, you have this point, and then you have this point, and then you look at different paths, and oh, I found a path. Right? I found this path, which is based on the least action principle. So, oh, actually, I should have written that over there, because the least action principle is what is exactly opposed to F equals ma. You could write this as delta of S being equal to 0. So if you want to have an equation for both, you could do this. But the formalisms are different. F equals ma is different from delta S being equal to 0. If you work with an actual acceleration, maybe F equals ma is just better for you because it's easier. You can get the force ready and everything, right? So if you know that this is a gravitational, or basically you work in the case of the acceleration being negative g, maybe this is just easier. But the Lagrangian formalism gives you the least action principle. So if you talk about a rubber band or something that you talk or think about in terms of different paths and what action there is, then maybe the Lagrangian formalism is better. And also the other interesting idea is, while both yield the same result, they kind of feel different. Newtonian physics feels different in this kind of way from Lagrangian physics, because they yield the same thing, but in a different way. And what you can, what the first thing that comes to mind is when you talk about this kind of stuff, is how easy it is to generalize this kind of behavior. In Lagrangian mechanics, is so easy to generalize which is different from Newtonian physics, which isn't as easy to generalize. So let's write that down. One might be easier to work with. One might be easier to general or easier to build upon. So these are kind of points that you have to keep in mind when basically choosing between theories. One might be more pleasing, more elegant in this way. And both provide, and this is interesting, both provide interpretation. Which are not necessarily equal. And this is where it becomes really interesting, because we have two theories that show the same thing. They produce the same result every single time in these kinds of settings, right? So you can't choose one over the other. There's no right or wrong in this case. There's only preference. But as Feynman puts it, it's very, very naive to neglect one forever, because sometimes one might be easier to work with, one might be easier to build upon, etc. And the interesting interpretation that comes from this, for example, here, is that force is directed to, in this gravitational sense, right? So everything falls down. So this Newtonian physics is more about falling down. Whereas this Lagrangian physics is not about falling down. There, at this point in time, there is no down, and down doesn't really matter. What matters is that this is in some sense the perfect way of falling down because it takes the least action. So this is not about falling down, but this is about falling effectively, so to speak. Which is totally different. This is about the force and what kind of way it drives you. But this is more about, well, what is the most efficient way of doing things. And in this way, both are interesting, both are important and necessary when working in physics. Because you can't take one over the other. And to end this video, I want to do one discussion of time dilation. In special relativity, as probably most of you know, the faster you move through space, the slower you move through time. Now, time dilation can be thought of as two different things. And this is the last thing that I want to present. If you think about Minkowski space, then Minkowski space looks like x, y, z, and t. So this is a four-dimensional space where the fourth component is time. Now, we can look at a postulate, and the postulate being nothing can move faster than the speed of light. If we just take this as a postulate, what we can deduce is that the length, if we take, I should do like this, if we take the velocities in each, sorry for that, if we take the velocities in each component and square it, this is x squared, or x dot squared, y dot squared, and z dot squared, which means this is the same as the square of the length of this vector plus the square of the time derivative. But now nothing moves faster than the speed of light, then this has to be less than or equal to the speed of light squared. So what happens here is if you have this inequality. So the bigger this is, the smaller this must be. Because the inequality has to hold. And if this is getting close to the speed of light squared, then this has to go close to 0, because otherwise the inequality is just not satisfied. And this is what we mean by time dilation. Faster through space means slower through time. Now you could say, okay, this is Minkowski space and all that, but is there any equivalent formulation for this? Because as we've seen before, both yield the same result, but one might be easier and so on and so forth. Now, is there another way of writing this? Is there another way of finding time dilation, so to speak? And there is. Think again about relativity. The energy in relativity, if we think about particles, is the sum over particles over the square root of p squared c squared plus m squared c to the power of 4, and this is all like I. And so if basically if the momentum is 0, you arrive at your beautiful E equals mc squared. But if the momentum is not 0, then you derive at something completely different. And this is where interesting physics comes into play again, because if we reduce this problem to just one single particle, that was not good. To just one single particle, we can say, oh well, maybe this is way bigger than this. So, if m squared, and I will say c is equal to 1, we work in the units where c is equal to 1, and we can get rid of this. Again, we could carry it around, but it doesn't really matter. If m squared is way bigger than p squared, then E would be equal to, we have that m is way bigger than than p squared, and we could take m squared 1 plus p squared over m squared. But this m squared can now be extracted, and we're left with this. We can approximate this famously by the Taylor series. The Taylor series of 1 plus x is then equal to something like 1 plus x over 2. And this is important. So we could use this approximation, which is valid because m squared is way bigger than p squared, which means this term here is very small. And it being a very small term, and the Taylor approximation around 0, making total sense here. Because then this approximation is pretty good. It's pretty accurate because the term is so small. Now what we obtain is that the energy is almost m plus mp squared over 2m squared, because I take m times this whole thing, which is then equal to m plus p squared over 2m squared, which is amazing. This is the formula that we always dreamed about, right? Because this, oh, not m squared, that doesn't make sense. Because this looks just like a normal kinetic energy. Now, what is in the other, what happens in the other case? If p squared, and this is where it becomes interesting, because p squared is connected to the momentum, which means this is connected to the speed at which things move. And time dilation corresponds to things being fast near the speed of light. So, or occurs there, I should say. So this is the case where we would expect time dilation, right? Now E is again the square root of m squared plus p squared, but this time around we actually extract the p squared. We do the same procedure, and we obtain 1 plus m squared divided by p squared. Rise. We can do the same approximation because p squared is way bigger than m squared, which means we can say this is very, very small. So this is approximately p plus m squared divided by p, divided by 2p. So they've kind of swapped places, right? So what happens here? And this is an interesting question, because how do we see time dilation? Well, what happens if you move very, very quickly? Well, since this, let's say, because the momentum contains of 3 different parts, px, py, and pz, so if pz becomes very, very large, so if pz is very big, but constant, we can, because it's constant, neglect this term. So basically, energy, because we're only interested in physics about energy differences, energy is almost the same as m squared over 2p. But now, pz is very, very big. And p is in the denominator here. So this becomes very small. But again, this kind of makes sense if you think about time dilation, but how do we get time? Well, what is E? What is the energy? If you think about quantum mechanics, then energy is connected to the difference or to the change in time. The energy, the Hamiltonian operator, works as a change of time. Now, if the momentum is large because one component of the momentum is large because basically it is shot in one direction, then this becomes very small, right? But then this becomes very small. So d by dt becomes very small. And I shouldn't say d by dt becomes very small, but differences in d by dt become very small. Because, as I said before, we kind of drop the p because we're interested in energy differences. And energy differences corresponds to differences here, which means how fast is time progressing, right? This is what difference means, how fast it goes. But in this case, the differences are very small, which means time dilation in the case where the momentum is very large. Again, this is just time dilation, but seen from a different point of view. This would be time dilation in a four-dimensional space where you have coordinates and you kind of just grasp the idea of a norm, right? Like kind of the length of this velocity vector. But down here, you actually think about it in terms of energy, which is important. So you think about energy. So this is easier to work with when you want to work with energy, when you want to think about mass as well, when you want to think about inertia and all these kinds of things. And it is very, very important when you want to discuss different methods, right? Different speeds. And time dilation is just one effect that we see here. So, time dilation is obtained in two different ways, but one is definitely, as you can see, more complicated, more intricate, but even in a way more elegant, at least to me, and also uses energy, mass, momentum, and it uses all these interesting things that you can easily work with and generalize. So again, this one might be the first interpretation might be easier to work with in terms of presentability, but the second is definitely easier to build upon, and I think it's more elegant. But well, that's just me. And they provide different interpretations because this one you can think about points in space actually moving mathematically because you just have a four-dimensional manifold and you think about this thing moving and you think about tangent vectors and velocities and all these kinds of things, which is amazing. But down here you actually do more physics. Of course you do some approximation, but there's more physics here. There's more interesting stuff in terms of mass, inertia, energy happening. Let's summarize this. What we've seen today is that mathematics, at least to me, and I would propose that, is a language of ideas and logic that uses principles of ideas, right? So principles that the same kinds of ideas that we had in one field of mathematics applies to another as well, if it's just translated well enough. It also is like a building block, but physics uses mathematics, but is then asked to interpret this mathematics, as we've done here, because we've interpreted this term, the d by dt, in the case that p is very large, to become what we mean by time dilation. This is not something that mathematically is completely obvious. The physics has to, or the physicist has to do the work of actually interpreting mathematics. And both of them, at the end of the day, are just sciences that use ideas. There is just no right triangle that I can draw, but I certainly can think of one, which is the important part. Maybe I have, well, I hopefully didn't bore you to death with this. Hope you enjoyed it, and check again next time. Bye bye.